Hi, welcome to my channel. In the last video on digital electronics, we defined the basic logic gates AND, OR, and NOT. And we defined the Boolean expressions for the outputs of each of these logic gates. And if you recall, X output for an AND gate in Boolean algebra is written X is equal to A and B. And for the OR gate, X is equal to A or B. And for the NOT gate, which is a single input device that acts on a single variable, X will equal to X naught. So it's the opposite. It inverts the input variable. In this video, we're going to build on this information, and we're going to show how one Boolean algebra can be used to describe the output of any logic circuit. Given a Boolean equation, we can convert it to a circuit. And Boolean algebra can be used to simplify a logic circuit design. So any logic circuit, no matter how complex, can be defined using the Boolean operations of AND, OR, and NOT. So here's a basic example of how we would use Boolean algebra to describe the output of a simple logic circuit that contains two gates. So if we had an AND gate with two inputs, A and B, and the output of that AND gate fed into an OR gate, like so, and there was a third input here, we label C, and we wanted to find the output X here in a form of a Boolean equation. Well, we know that the output of the AND gate is A and B, and we know that the output of the OR gate produces the OR sum of these two inputs. So we will have A, B, ORed together with C. So the output of the OR gate is defined by X equal to AB ORed with C. Now this output can also be expressed as X equal to C or AB, since the order does not matter. Now, to avoid any confusion on the order of operations, it is understood that AND operations are performed first, unless there are parentheses, in which case the operations in parentheses are then performed first. So if we took the above equation and we said X is equal to C or together with A and B, and then we put parentheses around this, that would be a completely different circuit. So if we initially had the above equation, X equal to C or together with A, B, but parentheses redefined it like this, this would be a completely different circuit. This here would describe a circuit where we would have an OR gate with two inputs. We have an A and input C, and then that would be fed into an AND gate and AND with the B input. Now let's go on to how we express the operation of inverters in Boolean algebra. So inverters only operate on a single variable. It's just a single input device. So we have the symbol here for an inverter. And the way we express that in Boolean algebra is that we put a bar over the variable. So if we had a variable X as the input, the output variable x would be x naught, and the symbol is just x with a bar over it. And again, this acts on only a single input. So here are a couple of examples how we would express the inversion process using Boolean algebra. So if we had, for an example, an OR gate, a two-input OR gate, and one of the inputs we had an inverter, and the two inputs are variable A and B, the output expression for x would be A naught, the OR sum with B. So we have A, and here being fed into the OR gate would be A naught. Another example, if we had an AND gate, another two-input AND gate, and we had, again, inputs A and B, but the output had an inverter on it. The output here would be described as x is equal to A and B naught. Now notice the bar goes over A and B because both A and B are inverted here. Now we need to point out that this is not equivalent to having separate inverters on each input. So if we had an AND gate and we had an inverter on both of the inputs, that output expression would be defined as A naught and with B naught. These are not equivalent. In this case, we have A and B are inverted first and then fed through the AND gate. And in the first case here, the one above that, we had A and B, and then they were both inverted. So those two are not similar, or not equivalent. And that's an important concept because later we will see how why those two are not the same. So it's important that we see that A naught and B does not equal A B naught. So up until now we've been able to produce a Boolean expression from a given logic circuit. What if we had the Boolean expression to start and we wanted to know what the value of x would be for given input values? So if we were given the Boolean expression x equal to A naught BC, and that was AND with C or D naught, and we were told that the value for A was 0 and B equal to 1, C equal to 1, and D equal to 0. Well, let's just go ahead and plug those values in. So A is 0, so this is 0 naught, and it's AND together with a 1 and a 1, and don't forget the parentheses here, and we have C is equal to 1, and that's OR together with D, which is 0, and don't forget the inversion sign, the inverter sign of the bar. So 0 naught, so 0 naught is 1, and that stays the 1, that stays a 1. Now let's do the operations within parentheses. We've got 1 OR together with 0, we know that equals to 1. And then that has a bar over it. So not 1 is 0. So we have 0, going backwards here, 1 and 1 and 1. So this essentially is a 4-input AND gate, and we know that an AND output only produces a 1 on the output if all the inputs are high, or a 1. So for this, x will equal 0. So if we were to look at that as a logic symbol, we would just have an AND gate, a 4-input AND gate. We'd have 1, 2, 3, 4. And these are 1, a 1, a 1, and a 0. And that's going to produce a 0 on the output. When evaluating Boolean expressions, there are 4 general rules to follow. And they are: 1, perform all inversions of single terms first. 2, perform all operations within parentheses. 3, perform AND operations before OR operations, unless parentheses indicate otherwise. And 4, if an expression has a bar over it, perform the operations of the expression first and then invert the results. So we've determined the Boolean expression for a given logic circuit, and we've evaluated the output of a Boolean expression for given variable values. But we can also derive a logic circuit just from the Boolean equation. For instance, if x equal to a, b, and c, it's sort of intuitive that this is just a 3-input AND gate. So we would have an AND gate with 3 inputs, A, B, and C. Same if we had x equal to A or B or C. This would be a 3-input OR gate, like so. 1, 2, 3. We got A, B, and C. Put them in here too. And this would be X. And the same reasoning can be extended to more complex circuits. So if we had x equal to AC, or together with B naught C, and that was or together with A naught BC. So let's see if we can come up with a logic circuit for this Boolean expression. Let's see, we have an AND gate, 2-input AND gate. We have A, and we have C, and we have another AND gate here, and we have one of the inputs is B naught. So we have B, and this is B naught, and then we have C again, and then it looks like we have a 3-input AND gate. 1, 2, 3 inputs, and this is A. This will be A naught. So there's an inverter here, and this is C. And these all feed into a 3-input OR gate. So this would come down here. And this is X out. And that one was sort of intuitive. You can see that each one of these terms is an AND gate, and they're all fed into a 3-input OR gate. Now we want to reiterate that any logic circuit may be described using the Boolean operations of AND, OR, and NOT. And these three operations can be combined to define two additional logic gates and their Boolean expressions. These gates are used extensively in digital circuitry, and they combine the AND, OR, and NOT operations. And these two additional gates are the NOR gate and the NAND gate. So let's start off with the NOR gate. The NOR gate combines the operation of an OR gate and an inverter. So if we were to show this with the OR gate and the inverter, it would just look like this. There's an OR gate, and it's followed by an inverter or a NOT gate. So if this was A and B on the input, this was X, the Boolean expression for X would be A or B NOT. And notice that the bar goes over both A and B. So essentially, a NOR gate is equivalent to an OR gate followed by an inverter. So let's investigate the truth table for a NOR gate. Let's first write down the truth table for an OR gate. So if we had A, B, two possible inputs, write down all these combinations here, 0, 0, 0, 1, 1, 0, and 1, 1. The output for X would be 0, 1, 1, 1. And for X naught would be 1, 0, 0, 0. So we see here that it's the complete opposite of an OR gate, where an OR gate produces a 1 when any of the inputs is a 1. The OR gate produces a 0 when any input is a 1, and it produces a 1 when both inputs are 0. The NOR gate does have its own symbol. So instead of having it shown as an OR gate followed by an inverter, you will see it as just like an OR gate, but it has a small circle here at the tip indicating the inverter. And the output again, X is equal to A or B naught. Now at this point I'd like to introduce the concept of a double inversion. So if we have an OR gate followed by an inverter, we have A and B. We see that A or B not describes the output X, and we've defined that as a new logic gate, a NOR gate. Well, if we follow that with another inverter, in essence we'd have X equal to A or B double naught. And that just brings us back to where we were with an OR gate. So X would equal to A or B. So the double naughts cancel each other out. And it would be the same for if we have a NOR gate using its own symbol, and we follow that with an inverter or a NOT gate. That would just give us X equal to A or B. So a NOR gate followed by an inverter gives us an OR gate. So now let's move on to define a NAND gate. The NAND gate is equivalent to an AND gate followed by an inverter. So if we have an AND gate, and then we follow that with an inverter, this would be equivalent to a NAND gate. So we have A and B, and this is X. Here X would equal A and B, and here X is equal to A, B, naught. So remember, the truth table for an AND gate is A and B. It produces a 1 only when both inputs are a 1. So if this is X, this is 0, 0, 0, and 1. And for a NAND gate, it produces a 0 when both inputs are 1. And it has its own symbol too, and the symbol for the NAND gate is the AND symbol with the small inverter sign on it, like the NOR gate. That's how you usually see it. And X is equal to A and B naught. So we'll end this video here. We covered quite a bit of information. We showed how we can use Boolean algebra to define the output of a logic gate or circuit, and we derived a logic circuit from a Boolean equation, and we set up some rules for evaluating the Boolean expression. We also solved the Boolean equation for given input values, and we introduced two new gates, the NOR gate and the NAND gate. So hope you found this video interesting. Please subscribe and/or comment, and thanks for watching.